Welcome to this explainer. Today, we're diving into the absolutely mind-bending science behind the world's most prized metal, gold. You know, what seems like just a simple, shiny piece of jewelry is actually a total masterclass in extreme physics and dynamic chemistry. We've got a lot to cover, so let's jump right in.
Let's kick things off with an everyday mystery that's actually puzzled humanity for millennia. I mean, if you stop and think about it, most metals we pull out of the ground are just grayish or silvery, right? And most of them degrade over time. Iron rusts, copper turns green, silver tarnishes into this dull, dark gray. But gold is brilliantly, unmistakably yellow. Plus, it's virtually immortal. You can pull a gold coin from a sunken shipwreck after literally hundreds of years, and it shines exactly like the day it was minted. So why is that?
We all instantly recognize the beautiful, immortal shine of a raw native gold nugget, just like this one. But to actually understand how it works, we have to completely change our sense of scale. We literally can't figure this out just by looking at the metal in our hands. To find our answers, we're going to have to zoom way past the macroscopic world and dive straight into the atom itself. Oh, and we're bringing Albert Einstein along for the ride.
Section 1. Einstein inside the atom. So, the real secret to gold lies in a fascinating field called relativistic quantum chemistry. Now, don't let that name intimidate you. It simply means we're using Einstein's famous theory of relativity, E equals mc squared, linking energy, mass, and the speed of light, to understand how chemicals behave. For the longest time, chemists didn't really think relativity mattered much for ordinary chemical reactions. But researchers, like a team out of Heidelberg University, have proven that for heavy elements on the periodic table, you absolutely cannot explain their basic properties without Einstein.
Okay, so this builds into this totally amazing atomic chain reaction. Let's break it down. Step 1. Gold has a massive atomic number of 79, meaning it has a huge, highly positive nuclear charge. This heavy nucleus pulls incredibly hard on its innermost electrons. Step 2. Because of this extreme pull, those inner electrons are forced to whip around the nucleus at unimaginable speeds just to keep from crashing into it. Step 3. According to relativity, as an object approaches the speed of light, its mass actually increases, so these electrons literally become heavier. And finally, Step 4. Because these electrons are now heavier, their orbital radius drastically contracts, shrinking by roughly 22%.
But the absolutely crucial point here is this insane number. For that mass increase and shrinking to happen, the inner electrons of a gold atom have to be traveling at 58% of the speed of light. I mean, just think about that for a second. Inside the completely stationary gold ring on your finger right now, electrons are zooming around at over half the speed of light, causing a relativistic warp in the atom's very structure. Pretty wild, right? So we have a warped, shrunken atom. Let's see how this incredible speed and shrinking atomic radius actually creates the unique color we see on our jewelry.
Section 2. Why gold is yellow.
Right, so because of those relativistic effects we just talked about, the outer electron shells of the gold atom get pulled closer to the nucleus. Specifically, it's gold's 6s orbital that shrinks. And as it shrinks, the distance between that 6s orbital and the 5d orbital beneath it gets much, much smaller. This closing of the gap alters the exact amount of energy required to make an electron jump between them, and that in turn completely shifts exactly which wavelengths of light the gold atom swallows up when light hits it.
This perfectly illustrates the real-world impact of that microscopic shift. Just look at gold compared to its periodic neighbor, silver. Gold's shrunken orbitals mean it absorbs lower-frequency light, specifically blue and violet visible light. Now, in human vision, yellow is the complementary color to blue, so when gold absorbs the blue, the light that bounces back and hits our eyes is this brilliant, iconic yellow. Silver, on the other hand, it doesn't have quite enough nuclear charge to shrink its orbitals as extremely. Its 4d and 5s orbitals remain further apart. Therefore, silver needs higher energy light to make that electron jump, which means it absorbs in the invisible ultraviolet spectrum. Because it reflects all the visible colors right back at us, silver just looks colorless, or, silvery. So the big takeaway here? Gold is literally only yellow because of Einstein's theory of relativity? Kinda mind-blowing. Anyway, we've solved the color mystery, but what about its immortality? Let's zoom in on the physical surface of gold to see how it fights off decay.
Section 3. The Anti-Tarnish Atomic Shield.
For a really long time, we all just assumed gold was chemically noble and just kind of passively ignored oxygen. But researchers at Tulane University recently discovered that gold actually plays an active, dynamic role in keeping itself clean. As Matthew Montemore, an associate professor there, explains, the surface atoms automatically shift their geometry. They literally rearrange themselves to protect the bulk of the metal beneath.
By shifting into these protective geometric patterns, the surface atoms create the ultimate physical barrier. Normally, when an oxygen molecule lands on the surface of most metals, it easily splits apart, bonds with the metal atoms, and creates an oxide. That's what gives us rust or tarnish. But gold's automatically rearranging surface geometry literally blocks those oxygen molecules from successfully splitting and bonding. It acts like a completely self-protecting atomic shield.
And the efficiency of this shield is just absolutely staggering. Computer simulations from the Tulane team showed that this natural geometric rearrangement slows down the oxidation and tarnishing process by up to 1 trillion times. 1 trillion. That right there is exactly why a Roman gold coin dug out of the mud today shines exactly as brightly as it did 2,000 years ago.
Section 4. Why your jewelry tarnishes. So if pure gold is virtually immortal and perfectly shielded against oxygen, you might be looking down at your hand right now wondering why your own personal jewelry sometimes leaves dark smudges or green marks on your skin. Well, the reality is that while pure 24-karat gold is incredibly resistant to the environment, mechanically it's just way too soft. It scratches easily, it bends under pressure, and if you wore a pure 24-karat ring every day, it would quickly warp completely out of shape. Because of this, jewelers are forced to mix pure gold with harder base metals to create a much stronger alloy.
As you can see, the carat system is essentially just a measure of how much pure gold remains in your jewelry. 24 karat is 100% gold, meaning zero tarnish risk. But look at 14 karat gold. It only contains 58.3% pure gold, leaving over 41% to other alloyed metals. At 10 karat, less than half the metal is actually gold. The rule of thumb is, the lower the carat, the less gold is actually present to act as that atomic shield, leaving those added alloy metals completely vulnerable to the environment around them.
So, when you see discoloration, it isn't the gold decaying at all. The true culprits are always the added metals. Copper, which is what gives rose gold its warm hue, reacts with your sweat to turn green or brown. Added silver reacts with sulfur in the air to form a black layer. Zinc and nickel in white gold will oxidize against acidic skin. And everyday things like chlorine from swimming pools or ammonia from household cleaners actively attack these softer base metals, breaking their chemical bonds. It's a reaction happening entirely to the alloys hiding inside your jewelry. The gold itself is just fine.
I want to leave you with this really provocative thought from the researchers at Tulane. Now that we understand exactly how gold's dynamic surface rearranging acts as a shield against oxygen, chemical engineers are trying to figure out how to reverse it. Think about it. If we can control the shape of the gold surface and prevent it from forming that protective barrier, we can actually force this stubbornly immortal metal into becoming a highly reactive catalyst. By breaking its defenses, gold could become an absolutely crucial, hyper-efficient tool for driving the clean energy technologies of the future. It's wild to think that what we've prized for thousands of years just for sitting still and looking pretty might very soon be put to work to save the planet. Thanks so much for joining me on this explainer, and keep questioning the science hidden inside the everyday objects all around you.